Okay, it's recording now.
Okay.
So
just share the screen.
Sure. In the meantime, hello everyone. Welcome to the first department seminar of the year and of the semester. Very happy to have Saurav today. Saurav needs no introduction. So I guess we can get started with the talk. As I was mentioning earlier, the thing that I find most fascinating about today's talk is that this is based on work that started all the way back in 2006. Some of us were in high school at that time. So I'm really looking forward to this. Thanks, Saurav.
Okay. Thanks, Venkat. Thanks for that nice fact. I wasn't. I mean, that definitely is very interesting. I had no idea. Yeah, definitely makes me realize how older I am. But thank you for it's a pleasure to speak to my colleagues and students in the department. This is a talk on imagining a new compiler architecture, the compiler as a database of optimizations. This joint work with my PhD advisor, Alex Aiken, and my PhD advisees, Manjeet Dahiya, Shubhani, and Abhishek Rose, all of whom are current or past PhD students at IIT Delhi. Also, there are several past master's and bachelor students who have contributed to the work that I'll present today. So let's start with the problem. Hardware architectures are innovating at a much faster pace. For example, many core, SIMD, memory hierarchies, complex ISAs, on-chip accelerators, etc. But it is much harder for compilers to keep pace. And because compilers are slow to catch up, architects are forced to reconsider their ideas. An architectural feature that the compiler does not support is basically used by a very few expert assembly programmers only, and so does not make the desired impact that the architects hoped for. And so pretty much, this picture shows that the architects are kind of tied to the compiler. Compiler's moving slow. Architects could move much faster, but they're kind of just waiting for the compiler to catch up. To understand why compilers are so slow in responding to architectural changes, it is instructive to look at the complexity growth in compilers. This chart demonstrates the number of lines of code in the GCC compiler over time, starting from 1992. The number of lines of code has increased linearly, basically as fast as humans could develop it, as far as I can tell. Today, GCC stands at over 18 million lines of code, with an astounding amount of complexity. To steer and adapt this complexity to the changing architectural and hardware needs is daunting. At this point, I'm sometimes asked about this dip in the number of source lines of code at around 2016, 17, 18. And I checked this, and this is because a garbage collector named Boehm was deprecated at this time. So, I mean, it's nothing fundamental to the compiler development process. I mean, it's just a matter of fact that there was a dip, but you can see that still, the growth is pretty astounding. And that's as GCC. I mean, what about another compiler? So there's LLVM that was started in 2001. That has risen to popularity both because of its cleaner abstractions and permissive licenses vis-a-vis GCC. Indeed, LLVM developers have distinct advantages over GCC developers by virtue of starting late and thus leveraging modern tools and techniques and also avoiding known pitfalls. Yet the development model hasn't changed, and we see a similar growth in complexity for LLVM 2. Here I show the lines of code in LLVM's core components, just the core components, not the entire LLVM. The entire LLVM is much bigger. So when I say core components, I'm basically looking at the include and lib directories in LLVM source code over time. Once again, we see a linear increase in complexity in just the core components, and that is showing no signs of slowing down. The total lines of code of LLVM's core components stands at over 3 million today. Moreover, the graphs I showed earlier are only for a small set of languages supported by GCC and LLVM. The set of all languages is much bigger. The reason we have so many languages is because while some are easier to program, others are easier to optimize for performance. Also, some languages are domain specific. Moreover, the number and types of hardware substrates has been growing at breakneck speed too, from FPGAs to neuromorphic to accelerators, GPUs, etc. Once again, some are easier to program, others are easier to optimize, and yet some others are domain specific. Necessitated by the end of the Moore's law, we are witnessing an unprecedented rate of increase in the number of languages and the number of hardware architecture. So it's nowhere near slowing down. This rate of increase in diversity on both ends is not just necessitated by the end of Moore's law, but also by the increasing number of computing applications being discovered over time. And AI is a good buzzword to represent many of those computing applications. A key component of this picture, which can help us tackle this complexity in an easier manner, is the compiler. Yet, as I said before, the in compiler development is too slow to meet these growing demands. If we consider the program specification as the problem to be solved and the corresponding optimized assembly implementation as a solution, then traditionally this distance from the problem to the solution is covered by compiler algorithms that have been carefully developed by expert human programmers. Because the teams of human programmers are limited by the amount of complexity they can tackle, we are bottlenecked by the pace of compiler development, as was also evident in the graphs we saw earlier. One potential solution to this problem is to try and get machines to help us in this compiler development task. This may look reminiscent of what we call AI, etc. as well, but there's a totally different context, I guess. An overwhelmingly large fraction of the compiler complexity is its optimization logic. So if we could get the machines to automatically identify optimization opportunities, that would relieve the human programmers of this complex task and could potentially make the compiler development process faster. I show a picture here. Here we have two sets of algorithms. One set are the inductive synthesis algorithms that use certain heuristics and search strategies to automatically propose candidate solutions. Recall that a solution is basically an optimized assembly implementation. You can imagine that these inductive synthesis algorithms are approximate. Example, they may be based on machine learning techniques, if you will. And so the candidate solutions may be incorrect. However, a compiler cannot tolerate an incorrect optimization. And so we use a validator, also called an equivalence checker, that checks every candidate solution. This is the second set of required algorithms in this design. The equivalence checker checks the candidate solution for equivalence against the program specification. If it is able to prove that the two are equivalent, we obtain an optimized solution. On the other hand, if the equivalence checker is unable to prove that the program specification and the optimized assembly implementation are equivalent, it should typically generate a counterexample that demonstrates this inequivalence. A counterexample here is just a program input that would cause the specification, the problem, and the implementation, the solution, the candidate solution, to behave differently. This counterexample can then be used by the inductive synthesis algorithms to appropriately fine-tune their search, so better candidates are generated in future. This vision has been painted by several researchers in a common theme of work called program synthesis and super optimization. So this is not just one research group working. There are many people who have kind of painted this vision. Unlike current compiler optimization algorithms, a super optimizer is interested in finding the optimal implementation for a given problem, and hence the name super optimization was coined in 1987 by Henry Massillin. So just in case you're wondering about this word super optimization, it is basically because the first time such an inductive synthesis algorithm was proposed, it was for searching for an optimal solution, as opposed to what current compilers do. I mean, there are absolutely no guarantees about optimality in what the current compilers do. They are basically best effort algorithms. So that's why the name stuck on, and we still call them super optimization. In our work, we're not really constraining our inductive synthesis algorithm to be necessarily finding optimal solutions. They should hopefully find better solutions than what we already know. For inductive synthesis, several algorithms have been proposed, starting from brute force enumeration, that was original Massillin's work, then stochastic search, learning from examples, mutation-based learning, algorithms based on constraint solving, neural networks, etc. In fact, you can plug any fancy technique you like here, because the algorithm only needs to produce candidates, but hopefully good candidates. In that sense, these inductive synthesis algorithms are noisy and approximate, unlike the current correct by construction algorithms used in current compilers. The complexity of current compilers basically stems by this correct by construction approach that needs to be followed. And we are kind of relieving the compiler developer to not have correct by construction algorithms. You can kind of do something which is kind of just approximate, and maybe it works and maybe it doesn't. But irrespective of the noisy synthesis strategy, we would always require an equivalence checker that would act as a gatekeeper for these learned transformations. The better an equivalence checker, the more optimizations we could potentially learn. Thus, the power of a super optimizer is in a big way dependent on the capabilities of an equivalence checker. For example, if an equivalence checker incorrectly discards a valid solution, our system will never be able to identify and learn the corresponding optimization, no matter how good your inductive synthesis algorithms are. So in a big way, equivalence checker is kind of the backbone of the super optimizer. So let's step back and compare this development model to the traditional development model for a compiler. In the traditional model,
Saurav?
yes.
Quick question. So this equivalence checker, it could have errors on both sides, or is it usually one side is always error-free and the other one is?
Okay, that's a great question, and yes, it needs to be what we call sound, and I'm going to come to that quickly. It needs to be sound. So if it says yes, then they better be equivalent, because recall, compiler cannot tolerate wrong optimization.
Right.
But it's okay if it says no every now and then. Okay, so it needs to be reliable on one side at least.
Right. Okay. Yeah,
okay?
Thanks.
Thanks for the question. So let's step back and compare this development model to the traditional development model for a compiler. In the traditional model, an engineer gets an optimization idea. She codes it up, and then it's reviewed by experts, right? Sometimes the proposal is rejected for various reasons, such as the optimization is too complex for the benefits it entails, or it's too specific to a certain programming language or to a certain architecture, or because the optimization requires coordination of a lot of different compiler passes, and that would probably require a complete overhaul of the compiler. It commonly happens, and so on. And so all this work has gone into trying to get something into the compiler, but really we have not made any progress, and eventually all that work has been rejected. So overall, too much human effort has been wasted in this exercise without making much progress. On the other hand, if the engineer is lucky, the optimization idea gets accepted after painstakingly careful reviews. But wait, even after all this careful reviewing effort, compiler bugs remain common. Most compiler bugs are caused due to overlooking of corner case situations resulting from integer overflows, memory overruns, undefined behavior assumptions made by the optimization algorithm, etc. These corner case situations are really easy to miss for human reviewers, but would typically not escape a mechanical validator like an equivalence checker. You would be very surprised to know how common compiler bugs are. Typically, people think that compilers are usually correct, but if you just look at the number of bugs that get accepted and filed every year or every month, you would be surprised to see how common this thing is. So the proposed development model, which we have also been referring as the super optimization model, looks much different. Here, the inductive synthesis algorithms are rather carefree in what they propose. For example, they may throw all aliasing considerations out of the window and kind of ignore all corner cases and so on. In that sense, the developers of these inductive synthesis algorithms do not need to be very sophisticated compiler experts. They are allowed to just try and see. These people here are just trying some random stuff. The onus of maintaining the correctness now lies with the equivalence checker. The equivalence checker would either reject the candidate solutions or accept them. In case it accepts the candidate solution, it caches the problem solution pair for future use. This caching basically represents the problem solution pair as a pattern replacement rule. These pattern replacement rules can then be exposed as a table of potential peephole optimizations to the compiler. Here is an example of a pattern replacement rule taken from Henry Masselin's original super optimization paper titled A Look at the Smallest Program in 1987. Here, the pattern is the code for the signum function in C-like syntax. So if it's x greater than 0, return 1, that's blah, blah. And the replacement is the corresponding optimized assembly implementation for the Motorola 68020 processor. Notice that the assembly implementation does not contain any branches and would typically be hard for a human-coded compiler to generate. However, such implementations are easier to generate for a super optimizer. In my PhD work with my advisor, we generalized this approach to more permissive pattern replacement rules. For example, the pattern replacement rules could have memory accesses like the one showed on the top. Importantly, this work was targeted towards the development of peephole optimizers for x86 assembly code. And thus is slightly different from our original proposal where we expected the program specification to be in a higher level language. Regardless, in this work, the super optimization techniques were geared towards the automatic generation of people optimizations and not just full solutions as done in the original Massillon paper. So for example, all these are just people optimizations, and how a people optimization basically says here is a sequence of instructions that should be pattern matched with code, and where you can probably do register renaming. And then if you see this pattern, you can replace it with this. Further, the pattern also has, we also supported, what are another kind of pattern matching kind of feature was what are the live registers at the end of the sequence. So if the live registers are only R1 and R3 and not R2, then it's possible to replace it with a single instruction exchange in the x86 architecture. We also supported branches, right? For example, this is jump, a conditional branch, and it's being replaced with a conditional move. Now, how do these people optimizations work? Well, this is a standard approach used in compiler and compilers, where you basically have a sliding window and you check whether the current sequence that is that is kind of selected by the window, does it match any of the patterns in my pattern replacement table? And if it does, then you basically try to trigger the corresponding replacement. That's what a people optimization is called. That's what a people optimization means. And this work basically generates automatically generates a table of people optimizations. Here are some more pattern replacement rule examples that were discovered by the super optimizer automatically. Here we see rules that involve the use of relatively new architectural features at that time, such as vector instructions and conditional moves. Notice that these pattern replacement rules also take into account the liveness information of assembly registers, as I just explained in the previous slide as well. Further, this work proposed the generalization of problem solution pairs to pattern replacement rules with symbolic constants. For example, you could have a pattern which said move $C0 EX and then decrement EX, and C0 could pattern match with any constant, let's say 1, 2, 3, or 4, 5, 6, or so on. And then the replacement could be move C0 -1 EX. So, I mean, the optimizer and the super optimizer were capable of learning and applying rules of this nature, where pattern matching is not just done on the name, but also on the constant value. All right. Now, because only acyclic patterns and replacement were considered in this work, the equivalence checker was realized by first converting assembly sequences into their logical circuits. So for example, this sequence here can be represented as a logical circuit, which basically transforms the state. For example, it kind of changes the value of memory pointed to by the EX register, and you can kind of represent it as a logical circuit. And then you can kind of give it to a satisfiability solver, an off-the-shelf satisfiability solver, which was available at that time and has significantly improved over the years. And today we have much more sophisticated satisfiability solvers than in 2006. The satisfiability solver returns either true, which would mean that the programs are equivalent, or false, which would mean that it's a counterexample. Okay, so this is what the previous work does. But this work on automatic generation of people optimizations is nowhere near enough for our proposed goal of replacing a human developed compiler with a super optimizer based compiler. First of all, one of the big limitations of a pattern replacement rule that I showed you is that it cannot reason about loops. This is a very important limitation because loop transformations are by far the most consequential transformations when we talk about runtime. And so if you cannot do that using this approach, then there's no hope of being able to replace the current compiler development model. Further, aliasing information is not captured. For example, if there's whether it's a heap access or a stack access, you should be able to reason that a heap access cannot alias with a stack access, and by that using that, you should be able to kind of get rid of some instructions. In this case, I'm just getting rid of the third instruction store because I know that it's already available in reg. It's already available in memory. The reg value and the memory address agree because heap adder cannot alias with stack adder. But if you don't have this aliasing information, this transformation is invalid. There are several problems to be solved to potentially realize a super optimizer based architecture for a compiler, but perhaps one of the most important problems here is the development of an equivalence checker that is capable of supporting loops and aliasing information, and that is what we focus on in our research. Recall that we said that the capabilities of the equivalence checker determine the power of the super optimizer based development approach. The equivalence checker needs to support checks for end-to-end equivalence between an unoptimized program specification and a fully optimized implementation without assuming any knowledge of the intermediate steps used in the transformation pipeline. That's a very important point. And that was not kind of considered by work that prior to ours. It needs to support loops, aliasing information, and all the general constructs of an imperative program language, such as function calls. Importantly, the equivalence checker must have no false positives, and this is, this answers Venkat's question. In other words, it must return true only for truly equivalent programs. In other words, the equivalence checker must be sound. A false negative is a situation where an equivalence checker returns false when the programs were actually equivalent. It is perhaps not possible to build an equivalence checker that is both sound and has zero false negatives, because the problem is undecidable in Turing's model of computation with an infinite tape. And I deliberately, kind of qualify this whole thing, with an infinite tape, because I kind of think that there's a lot of confusion in this, and I get asked a lot of questions here. The equivalence checker should aim to minimize such false negatives. All right, so this problem of equivalence checking has a well-known and important application in translation validation. Because compilers are so complex and may have bugs, a translation validator checks the source code against the machine code for equivalence. Because this is a well understood experimental setting, so translation validation work has been appearing all since the 1990s. Basically, everybody recognizes that compilers are too complex, they have bugs, so for critical applications, you need a translation validator, where they would just basically check whether they're equivalent or not. But here you can also assume what are the pipeline of optimization. So this is what the typical translation validation experimental setting would look like. We have been developing our equivalence checker in this context too. So we have been, because the other components of the super optimizer are not yet available. Scalability is an issue. So how do we check our equivalence checker? We check our equivalence checker in this experimental setting, which is a very well understood experimental setting. And it is an experimental setting where we can kind of, using which, again, by testing against which, we can kind of make our equivalence checker more and more potent. By the way, translation validation remains an open problem. It's not a solved problem. And the development of an equivalence checker that performs automatic translation validation would be a significant step forward in the development of provably correct compilers. So our work is not just kind of helping the super optimizer vision, but it's also, if we are able to do a full equivalence checker, then we are also making a dent in the translation validation space, which still remains an open problem. Our research over the past 8+ years has targeted this space, even though our broader motivations relate to a super optimization based compiler. So from here on, I'm going to just talk about this particular experimental setting, translation validation. And I just built up the case for this setting using super optimization, but now I'm just going to talk about equivalence checking in the context of translation validation. Consider the C program shown in red and the assembly program shown in C-like syntax in blue. The C program on the left uses a variable I to access arrays A and B. The assembly program on the right uses a register R1 to access arrays A and B. Given equal arguments and memory states at the program entry, equivalence checking involves proving equal return value and equal memory states at the exit. The question is how to show this through a proof. The proof will basically try to identify a lockstep execution of the two programs, such that whenever one program executes one step, the other program executes the corresponding step. These correlated locksteps in the two programs need to be identified such that it remains possible to relate the two machine states at all times, including the time when the two programs exit. For example, in this pair of programs, one iteration of the C program's loop may be correlated with one iteration of the assembly program's loop. And we may be able to make correlations in that case. So if one iteration executes and then simultaneously in lockstep, the second iteration executes, maybe we are able to say that I will be equal to R1 if we kind of execute it in that way. So that's what I mean by lockstep execution and relating the states through lockstep execution. Before we discuss equivalence checking, it is helpful to represent the program as a control flow graph or a CFG. A CFG node represents a program PC. So for example, C2 represents a program PC represented in this program. And a transition from C2, a, C, a CFG node represents, and each edge represents a transition. For example, the C2 node in the CFG represents the C2 PC in the C program. A transition from C2 to C3 is represented as an edge in the CFG. So this green thing here. And notice that the CFG representation is slightly different from the conventional CFG representation. Unlike the conventional representation, if you're a compiler person, the traditional conventional representation is where nodes are instructions and edges represent control flow. Here, nodes are PCs and edges represent instructions. So it's a slightly different representation of the program and a slightly different CFG that is more amenable to functional kind of analysis that we need. Nothing fundamental here. The edge is labeled with a transfer function, okay, of the corresponding instruction that determines the new state at the destination of the edge as a function of the machine state at the source of the edge. So for example, this, let's say this whole thing, C2 was one instruction, AI equals BI by 2 and I++. So that thing is basically represented as a function of which basically says how the machine state is kind of changed or mutated across this edge. So that's also called the transfer function. Also, every edge is labeled with the condition under which that edge is taken. For example, the edge from C3 to C2 is only taken under the condition I is less than 1024. Basically drawing a rectangle around the transfer functions, and for conditions, I'm not basically drawing any rectangle or anything. And also if the condition is true, then sometimes I just omit mentioning it, all right? Here I have mentioned it everywhere, but sometimes I just omit mentioning it. For example, going from C3 to EC, the condition is I is greater than or equal to 1024. From C0 to C2, the condition is true. I could have just omitted it as well. Okay, all right. So given two CFGs for a pair of programs like the one that I showed you, assembly and C, we are interested in identifying a lockstep execution. We will identify this lockstep execution automatically through the incremental construction of a product program. So I'm defining a term called product program that executes both programs in lockstep. So for example, in the product program, I'll say first execute one iteration of C program, then execute one iteration of the assembly program. And this program will be called the product program. A product program is a program that executes both programs in lockstep. For example, the product program may execute one iteration. Okay, I already said that. The product program correlates the transitions in one program with the transitions in another program as though they execute correspondingly in lockstep. For instance, the transition from C0 to C2 needs to be correlated with some edges of the assembly program. And in this case, let's say we decided somehow magically, and how we are going to do that, that's exactly what I'm going to show you later, is correlated with, let's say, A0 to A2. The correlations are also represented using a control flow graph that represents the lockstep execution of the two programs. The entry node of this control flow graph, C0A0, represents the condition that the first program is at PC C0 and the second program is at PC A0. We call this control flow graph on the right the product CFG. Further, the edges are added to the product CFG that encode the correlations. Here, the outgoing red edge from C0A0 to C2 shows the execution of the C program from C0 to C2. However, we have not yet correlated this edge of the C program with an edge of the assembly program yet. For example, we do not know what PC to correlate with C2 in the assembly program yet. In this product CFG figure, this correlation is completed by correlating the edge from C0 to C2 with A0 to A2. The C program's edge is shown in red while the assembly program's edge is shown in blue. In general, it is hard to determine which path in the C program to correlate with which path in the assembly program in lockstep. The relations between the states of the two programs are added as invariants at the endpoints of these correlations. For example, at C0A0, just before the program starts executing, we can assume that the arguments of the two programs are equal. Similarly, we can assume that the heap states are identical in both programs at entry for the programs to be equivalent. As we construct the product CFG correlations, we can also infer the invariants at the intermediate nodes. For example, in the current product CFG, we can be sure that whenever control reaches C2A2 through the lockstep execution of both programs, the variable I in the first program will be 0, and the variable R1 in the second program will also be 0. In addition to I and R1, we can also infer that the heap states were identical at C0A0, and so they will remain identical at C2A2. These relations between variables of the two programs are also called the invariants in the product program. An invariant in the product CFG or product program, I'm also using the word product CFG for the control flow graph of the product program, is a predicate that will always hold whenever of the product program reaches that point. The algorithm then proceeds by correlating loop transitions along with updating the respective invariants. For example, one iteration of the C loop body is correlated with one iteration of the assembly loop body. This correlation is shown as a red and a blue edge, this one and this one. And the assembly programs, and basically from C2 to C2 and from A2 to A2 for the two programs respectively. Notice that it is no longer true that I will always be 0 and at C2, A2, or R1 will always be 0, because now more paths have been added to the program. Because after an execution of the loop body, I may have incremented, and similarly R1 may have incremented. However, we can infer that even though both I and R1 are not 0, they're always equal in this product program. Note, this is what we mean when we say that the states of the two programs must remain related in the product program while identifying correlations of the paths of the two programs. Here, I is related to R1 in the product program. Also notice that it is possible to show that the heap contents remain identical at C2A2 irrespective of the paths taken by the product program. This property was possible only because the correlation chosen in the product program were carefully chosen to capture the lockstep execution of the two programs. Finally, the product program encodes that the C program exits if and only if the assembly program exits. The given product program is equivalent, and the given program pair is equivalent if the inferred invariants in the product CFG are strong enough to prove equivalent return values and heap states at program exit. In this case, this equivalence can indeed be proven through this product CFG we have constructed, because we know I equals R1, and then eventually we return I and return R1, the two programs respectively. We know that the return values are equivalent. Similarly, we know that the heap states are equivalent at exit. And so we have been able to prove equivalence and complete the proof. In the translation validation setting, the equivalence checker must be sound, as we already discussed. We have called this the property of zero false positives also. On the other hand, the problem of identifying the core transitions and required invariants for complex compiler transformations is undecidable in general in Turing's model of computation with infinite tape. And so completeness may not always be achievable. In other words, there will always be some negatives where we may not be able to find a proof even when the programs were actually equivalent. So there will always be some false negatives. Our research aims to reason about equivalence in scenarios where previous algorithms fail to compute equivalence in order to result in a more robust equivalence checker. Recall that a more robust equivalence checker results in a more powerful translation validator and a more powerful super optimizer. In our example, our algorithm should automatically identify which program paths in the C program are correlated with which program paths in the assembly program. Moreover, to achieve robustness, multiple path pairs with different possible transitions must be enumerated. For example, when we consider the candidate correlations for the loop edge from A2 to A2 itself, A2 to A3 to A2, we have multiple options. Either we could correlate one iteration of the C program, C2, C3, C2, or maybe two iterations of the C program, C2, C3, C2, C3, C2, or maybe 1.5 iterations of the C program, C2, C3, C2, C3, maybe, And so the algorithm needs to intelligently pick one of these candidate correlations, and that's a hard problem. Further, for robustness, a large number of affine invariants between the so yeah, I guess I just wanted that figure that I had on the previous slide basically shows what are all the possibilities, right? Further, for robustness, a large number of affine invariants need to be inferred between the variables from the C and the assembly program, and they need to be automatically inferred. For example, we said R equals I in the previous program. Now, actually, there are multiple possibilities. For example, R1 equals 2 into I, or R1 equals I plus 3, or whatever, right? I mean, there could be like a huge number of possibilities. And so for robustness, all these possibilities must be explored systematically and efficiently. A previous algorithm used a guess and check strategy for this. The algorithm picks each of these possible guesses. For example, it will pick R1 equals I, and then tries to inductively prove that whether it can be proven from the invariants at the previous node. And that proof will be discharged using a satisfiability solver the modern incarnations of which are also called SMT solver, satisfiability modulo theory solver. A previous so for example, here we could say that, this is the kind of query that we'll give to the satisfiable self-solver. We'll say, if I equals R1 at C2A2, then can I show that I equals R1 plus 5, after I traverse? So by the way, once I traverse this edge, I would have become I plus 1, and R1 would also have become R1 plus 1. So the query becomes, can you show, is it provable that if I equals R1, then I plus 1 equals R1 plus 5 plus 1? And we gave it to the SMT solver. The answer in this case is no. And so it gives the answer no. When it says no, it also generates a counter example, which is also called a model in the SMT solver parlance. In this case, for example, it can give the model 100. So if you just substitute the values 100, you will find that this whole thing evaluates to false. And so this counter example is a very important piece of information returned by the SMT solver that we use in an algorithm. So just keep this in mind. All right. So let's move on to our research contributions. The first key idea is counterexample guided invariant inference. Let's say one of the affine invariants that was required to prove equivalence was 2 into I equals R1. I just made the problem invariant slightly more interesting. Instead of I equals R1, let's say 2 into I equals R1, because on the assembly program, let's say the R1 is getting incremented by 2. Here we have made the, so this is slightly different from the previous example, but I guess, we want to infer this invariant 2 into I equals R1. How do we do that? In static equivalence checking, one can potentially enumerate all 2 to the power 32 possibilities, let's say, of this shape, which is, some C1 into I equals R1, but that's going to be too expensive. We have proposed a counterexample guided inference technique which involves executing the concrete mappings returned by the solver and using the execution output to infer the required relations instead of an expensive guessing procedure. So here is how it works. For instance, say one of the counterexamples returned by the SMT solver was I equals 0, R1 equals 0. So this counterexample, when executed on the C program path, so notice that this actually is a loop because C2A2 is just going to C2A2 again. So it's actually a loop, though I have kind of unrolled the loop a little bit here. And so then it goes again over it, and then I get 1, 2. Then maybe it goes again over it, and I get 2, 4, and so on. And then I can use these data points to kind of use some kind of linear algebra, and basically this is called bit vector affine algebra. And then basically say, can you kind of construct an invariant from these data points? And this kind of technique works really well to infer affine invariance of the form of something into some summation ai xi equals 0. That's an affine invariant, where xi's are the unknowns here. And in this case, xi's would be I and R1, and it kind of emits an invariant. So this work was based on work was published in SAT 2018. Moving on, the second key idea is counterexample guided correlation. During the incremental construction of a product CFG, we recall that we need to pick one correlation out of all possible correlations to expand further. So recall that when we wanted to correlate A2 to A2, we could have kind of put C2 to C2 or C2 to C2 to C2, I mean 2 unrollings or 1.5 unrollings and so on. And we don't know which one to pick. We propose a counterexample guided correlation algorithm, which involves executing the concrete mappings on all possible correlations and then inferring the strongest possible relations using the execution output. So we already know about the invariant inference algorithm. Using the invariant inference algorithm and the counterexamples, we will kind of infer the invariants at C2A2 using for all these possibilities of correlations. For example, if the concrete mappings obtained 0, 0, 1, 2, 2, 4, the fine solver will infer the invariant 2 into I equals R1 for one of these, right? And for the others, it will probably infer something else and so on. So let's say the inferred invariants were sum equals R2 for this word possible, for the first possibility. For the second one, it was sum equals R2 and I equals R3. And for the third one, it was sum equals R3. Now, which one of them is the most promising? Out because there are, I mean, the invariant that we have inferred in the middle one is kind of the strongest. It's correlating both sum and I. It is kind of, doing stronger coupling between the two programs. That seems more promising. The other ones basically just, being able to correlate sum, but not I. And so that's basically the key idea here. This will be ranked higher in our kind of search for proof. So this work is based on work published at OPSLA 2020, and I'm going to explain it more clearly with more examples now. So consider this example program on the left. Here there is a single program that iterates from 0 to len, and we also have mid equals len by 2. The body of the loop does something different for I is less than mid. So for example, it does sum plus equals CAI, and it does something different for I is greater than equal to mid. An optimizing compiler typically splits the loop into two loops as shown on the right, and this is called this loop splitting optimization. The first loop iterates from 0 to mid. The second loop iterates from mid to len, but the bodies remain identical. This is just one of the transformations that a compiler does. Next, the optimizing compiler transforms both loops using the loop unswitching transformation. Here what it has done is, look, in the first loop, I'm only iterating from 0 to mid. So the second statement is pretty much redundant. Moreover, I don't need to check whether I is less than mid. I'm sure that I will always be less than mid. So I can just replace this entire body with just the body of the first if statement. Similarly, I can replace the second loop's body with the body of the second if statement. And so this is called the loop unswitching transformation. And this is what we get after loop unswitching. The next transformation of a vectorizing compiler involves unrolling the second loop. Notice that the second loop is well structured. It's just kind of iterating subsequent like consecutive elements in consecutive iteration. So it just unrolls them. This is what a vectorizing compiler does because it is a nice pattern. And finally, the unrolled body is vectorized, implemented using a single vector operation in the assembly code. So I'm not showing the assembly instruction for vectorization, but just take it from me that this A6 instruction here, xmm0 blah plus equals blah, is just kind of implementing this entire thing, entire body of 4 instructions in a single instruction. Also, in the assembly code, we have several types of register allocation and other transformations that I have not even shown so far. Okay, I'm just kind of focusing on some of the main transformations that a compiler will do, which are kind of very loop-like transformations. The two input programs that are given to our equivalence checker in this case are the original program, which was basically completely unoptimized, and the final vectorized assembly program. And it is expected to identify an equivalence proof automatically. Recall that we said without assuming anything about the pipeline. We don't know what steps were followed.
Venkata, there is a question by Sanjeeva.
Yes, Sanjeeva.
Before you started this section, you said that you have a way of ranking the invariance. This is not a total order in any case; it's a partial order based on implication. Basically the one in the middle was implied both the others. So in general, it would be a Boolean lattice, right?
So thanks, Sanjeeva, for that question. So actually, this is just a heuristic, by the way. I mean,
Okay. So I was just wondering whether your ranking was a.
So if you notice, I mean, they are not even comparable, right? Sum equals R3 and sum equals R2 are not even comparable.
Yeah. No, I was just saying that this is some if it's a heuristic, that's fine.
Yeah.
In the case of the when you went a little further up, you said that you have all these optimization, these transformations which the optimizing compiler does. And is there some way of saying that this order of optimizations gives you better performance than another? Multiple optimizations could apply at a particular place, but some sequencing might give you better performance than others. That is, let's say loop splitting before this. And
absolutely. So this is a well-known problem in compiler, and it's a really kind of annoying problem. It's a classic problem. It's called the phase ordering problem.
Right.
And the phase ordering problem, like there's been numerous papers written on phase ordering problem. Basically, people have done machine learning to kind of figure out what's the best way of doing this and so on. The state of the practice remains that, it's just intuition of the programmers that this is going to work better than others. So few thumb rules, for example, vectorization should be done after unrolling, and things like that. So that's what the state of the practice is.
Yeah, no, I was just wondering whether with each of these optimizations, there is some kind of cost in some let's say a semi-ring or something, which one can then compare. And then let's say we are going to consider sequences of 3 or 4 optimizations in a window. And it's like, doing your which association or which ordering is best in that. Is that what the machine learning things are doing, or?
Yeah, so actually machine learning, let's not worry about the machine learning guys, but let's say, actually there's a paper, so there's a super optimizer paper, and then there's a line of work called saturation by Soren Lerner and his group, and then Zachary Tatlock from UW and UCSD. And basically they have a technique called equality saturation. So what they do is basically they build a graph of equal programs. And they basically apply transformations repeatedly until they saturate the graph of this equality transformations. And then after the whole thing is saturated, then they pick the best one. So these kind of approaches have been proposed, and equality saturation is a good keyword to kind of identify these lines of work. Definitely there's a line of work here, but yeah, I mean, just because of the cost of running these algorithms, these are not unfortunately used in compilers today.
Yeah, also, I mean, the saturation may happen at a point where you're doing many transformations, and you may not want to. You may want a heuristic which is sort of just says up to, let me just do combinations of k such.
Right. You could kind of bound it by k as well. Yeah, absolutely. I'm not. Yeah. So yeah, I mean, so people do kind of what I call super DFAs and things like that, right? I mean, yeah. I mean, yeah, k bounded stuff. Yeah, that's a good point. I mean, I'm not able to recollect off the top of my head a k bounded piece of work for this saturation algorithm. Yeah, but yeah. I hope that answers your question. Or?
I mean, in general, for the algorithms people, it's more like, how much of this can I do in an online fashion versus, an optimal fashion.
Right. Yeah, no, that's an excellent point. Thanks for that. Okay, thanks for that question, Sanjeev. I'm glad that there was a question because I was just speaking. Okay, great. The point I was making was that the equivalence checker is basically given these two programs, and it's supposed to work on them. And indeed, our equivalence checker works on these programs. That's a good news. The entry node. So at the bottom, I show the product CFG that's constructed for this pair of programs automatically. The entry node of the product CFG is C0, A0. Then the transition from C0 to C3 is correlated with the transition from A0 to A2 in assembly, entry to loop head. For the first loop. Then, I mean, the transition from A2 to A2 is correlated with C3 to C4, so C3. So if I just show it here, the first loop, this is the first loop of the split loop, right? So A2 to A2 is correlated with the original loop, C3 to C3 to C3. I mean, there's only one loop on the left, right? And then if the first loop in the assembly exits, that's A2 to A6, A2 to A6, then the first program actually just follows one more iteration in the loop. So that's an interesting thing, right? It just follows one more iteration in the loop. And then when I'm in the second loop in the assembly program, then one iteration of the assembly program from A6 to A6 is correlated with 4 iterations of the C program. C3, C5, C3 to the power of 4. So to the power of 4 is shorthand for saying just concatenated 4 times. And then when the assembly program exits, then the C program, the lockstep correlation for the C program needs to be C3, C5, C3 executes 4 times. So take 4 iterations of loop and then exit. So all this is pretty complicated to automatically figure out, but our algorithm, which is counterexample guided, is able to do this. So let's see. So how is it able to do this? So we kind of construct the product CFG incrementally. Okay. So we already know that there's a correlation between C0 and A0. We then identify a correlation for the assembly edge A0 to A2. There is some A0 to A2. Here the correlation indicates that if any of the paths in the path A0 to A2 is taken in assembly, then some path in C0 to C3 is taken. I'm lighting a little bit of detail here. There's actually, but that's okay. I mean, just in case there's a question, I can answer it. Then after each correlation, we relax invariants at the destination node. So once we have done this kind of correlation, we figured this out somehow using this ranking procedure that I just showed, I just explained. We use an off-the-shelf invariant inference algorithm to infer a fine equality and inequality invariance on bit vectors and memory states. So we infer invariance at C3, A2. And then we correlate one loop iteration of the assembly loop. And now, because we have already inferred the relations at C3, A2, it helps us infer the relations across the next potential correlations, and then rank and so on. So that's how it works. It's an incremental construction process. So and now we have to kind of find the correlation for A2, A6. We already know the invariants at C3, A2. Using that, we rank, we infer invariants at C3, A6. There are multiple possibilities. We pick the best one using the ranking procedure that I explained earlier. Similarly, we continue this, and every time we do this, we kind of keep relaxing the invariance. And finally, we check the equivalence of return values under the inferred invariance. If the equivalence can be proven under the inferred invariance, we have obtained a proof of observable equivalence. Now, of course, the incremental construction I described earlier seems too easy to be true, so I'm going to get into a little bit more detail. In reality, we don't know which assembly path set to correlate with which C program path set. For example, I could potentially correlate A0 to A2 with C0, C2, C5. Or here is another possibility. Maybe I correlated with C0, C2, C5, C7, and so on. Right? I mean, there are multiple possibilities. Addition 3, they're actually in the fan out is typically on the order of 10 or 20 or something like that. If I pick one of these possibilities, then I have a similar choice in the next step. So let's say I pick the bottom one, then I have the similar choice in the next step. And so this is an exponential search space, and an exhaustive search would take millions of years to complete, even for small examples. No prior work before ours can handle these types of transformations that I described using the previous example. Our algorithm is able to handle this transformation and many more in an efficient manner. The central idea is that we use in our algorithm the idea of counterexample. During invariant inference, we make potential guesses for a potential invariant. We then check a guess by trying to prove that it holds on the incoming edges. If it holds on all incoming edges, then we have found an invariant. If it does not hold on some incoming edge, then we obtain a counterexample from the SMT solver, and that counterexample at a node. That's the important thing. Represents a potential concrete machine state that may occur at that particular node during execution. So in a way, what could have actually occurred during actual execution is being inferred automatically using these SMT solvers things. So counterexamples are basically being used as a proxy for execution traces here. Okay. For a proxy, this would involve valuations of variables for both programs C and A. Moreover, because the product program is executing in lockstep, we can expect the variables of the two programs to have some relations. Example, I and C always equal to R1 and A in the counterexample. So for example, I equals 5, R1 equals 5, I equals 1003, R1 equals 1003. The two primary ideas that allow us to navigate this large search space are counterexample guided pruning. Using these counterexamples, we can potentially determine that some correlations are obviously incorrect if we find that the counterexample produces inconsistent behavior on the two machines. So for example, let's say some counterexample shows that one program is printing hello and the other program is printing hi. Then obviously there's a problem there, right? I mean, that's a bad correlation that we have right now. And then the second idea is counterexample guided ranking. We use a counterexample guided heuristic to rank some potential correlations higher than the other. Depending on the behavior of counterexamples, we can identify that some candidates are more promising than others. I will show this in more detail. Let's say these circles represent counterexamples identified for two different correlations at the destination nodes, C2, A2. Based on the counterexamples, we tried and identify the possible affine relations. That's the infer invariance between the variables of the two programs. Let's say the inferred invariance on the counterexamples are sum equals R2, J equals R3, I equals R1 for the first correlation, sum equals R2 plus R1, I equals R1 plus 1 for the second correlation. One of them has affine relations for three different assembly registers, namely R1, R2, R3, the other has only for two. I think we've discussed this in detail. And so this is our ranking heuristic. We find that this performs remarkably well in practice. So that's the important thing. It works well in practice to identify the most important promising candidate at each step of the incremental product CFG construction. For our experimental results, we applied the counter algorithm to C programs and their x86 assembly counterparts generated through three different optimizing compilers, GCC, Clang/LLVM, and ICC, with and SSE 4.2 optimizations enabled. We were able to compute equivalence for a large fraction, over 90% of the programs in the test suite for vectorizing compilers, which represents one of the most challenging vectorization benchmarks. So what we have been able to show is that we are able to deal with vectorization very nicely with this kind of black box algorithm. Point to be noted, 90%. So 10% are still remaining. So it's still not a fully solved problem. Over the years, we have found several bugs in compilers and other softwares, such as the QEMU binary translator, a C library, and an SMT solver. So we have found bugs in the ICC compiler, GCC compiler, and these softwares as well. In all these cases, when how did we find these bugs? We were not actually looking for bugs in these software. I mean, rarely do we find bugs in these very well-used software. We usually expect bugs in our equivalence checker when there's an equivalence failure. And so in all these cases, when the expected equivalence proof failed, we try to identify the reason for failure. Typically, we would expect a shortcoming of our tool, but sometimes we found that the bug was in the program pair being tested. Except the GCC bug, all other bugs were previously unknown and were fixed immediately upon reporting by us. You can find more details on these bugs at this URL, compiler.ai/bugs. Now I'll talk about another related piece of work very briefly. And how are we doing on time? I think we are out of time. So I'm going to skip this. I mean, we kind of use the equivalence checking approach to also automatically generate debugging headers. And this is another major problem in compilers that, the compiler developers are tasked to maintain the debug headers. And if you are a developer, you must be commonly experiencing that you try to print a value and it says value optimized out, or it gives you the incorrect value. And so we, propose a partial solution at least, where we say, okay, we can kind of construct these, based on our equivalence proofs that we generate, recall these bisimulation proofs that we're generating, we can generalize them and kind of populate the debug headers automatically. We get these correlations and invariants in our proof. We use linear algebra and data flow analysis and update the executable debug headers. And we find, these are the summary of our results. So we find that for the test suite of vectorizing compilers again, we find that we can improve the debug headers by 73% for Clang LLVM, 75% for GCC. So they are really doing a lousy job right now, for at least for these benchmarks, and 12%. So pretty much we are able to completely make the debugging information almost nearly complete. And this is the gap between nearly complete and what exists today. 12% for Intel CC compiler, the ICC compiler. It's interesting to see that the commercial compiler is much more careful about maintaining the debug information, and that's why perhaps they charge money for their stuff. Okay, this work on automatic generation of debug headers will appear in CGO 2022. All right, so I'm at the end of my talk. Compiler development is hard, but increasingly important. I would like to believe that super optimization is a plausible solution. Equivalence checking is an important prerequisite, and our work is hopefully giving evidence that scalable algorithms for equivalence checking are possible, and also have several other applications such as debugging headers and so on. Thanks.
Thanks, Saurav. Great talk. Any questions? Okay, Ramanuj.
Yes, sir. So in the equivalence checker, you were talking about how it needs to be, like, if a solution is true, then it needs to be completely true. However, the solutions you were talking about were about providing counterexamples to some assignments. So isn't providing counterexamples, as a proof of that this doesn't work instead of, so isn't this opposite of that?
Absolutely. That's a great question, Ramanuj. And yeah, we are not always able to produce counterexamples. Okay, so sometimes we are able to produce counterexamples, but not always. If we were able to produce counterexamples always, we would have solved the problem of equivalence checking completely. So yeah, we hope to produce counterexamples. Let's just say that. So either we are able to produce a proof. We hope to produce a proof. If not, we hope to produce a counterexample. If none of them work, then we just have to live with it.
Sanjeeva, you have a question?
Yeah, I hadn't lowered my hand, but I mean, there's a question so sort of a lot of the possible I mean, sometimes you may not have an equivalent program which performs better than the program which you have, but in a limited context, so this program might behave the same. So how do you bring in that contextual information? So so that you can leverage better performance, even though the suggested program is not really equivalent, but in this limited context, it will behave equivalent.
Thanks for that great question, Sanjeeva. So yeah, I mean, indeed. So in the context, I mean, especially when I talk about super optimization, right? I mean, context is very important. For example, in the original 2006 paper, one of the pieces of context was what are the live registers, at the end of the sequence. And that's very important. That was very important, by the way, to be able to generate any kind of reasonable amount of optimizations and populate the people transformation table. So context is very important. And are we taking care of the context? So far we are not actually. So what we do is we kind of do equivalence at function granularity right now. So as I kind of because we don't have access to a super optimizer or anything like that, but we still have to develop our equivalence checker. What we do is we kind of do it in the context of a translation validator. And when we do it in the context of a translation validator, we first disable all the inlining transformations. We also disable other inter-procedural transformations. And then we basically do equivalence at function granularity. So in that way, we kind of don't have to worry about inter-procedural context. First of all, because we are doing the whole function, we don't have to worry about any intra-procedural context because we're doing the whole function. But further, we kind of the way the experimental setting stands right now, we are forced to disable inter-procedural transformations because we don't take advantage of the context. We are not aware, the equivalence checker is not aware of the context, whereas the compiler is. And that's actually something that we want to do very quickly. So that's in our kind of future.
So how easy would it be to code the context to throw it at an SMT solver or something?
Yeah, so I mean, definitely, like the context cannot be free form, right? I mean, it cannot be like an arbitrary predicate as an invariant at the entry or something like that. In my opinion, that's just not going to scale. So it needs to be, I think we need to basically come up with restricted forms of types. It's like come up with some kind of restricted types that we'll kind of use as context for inputs and outputs. Perhaps that context would probably be, for example, we actually do use some context. For example, we basically take care of the fact that if I call some function, is it going to modify any memory location or not? So is it a pure function or is it an impure function? So that amount of context we are still actually doing, and it was important for us to be able to get the results that we have, to have that amount of context. We could probably also have context which says, okay, things like range analysis or something, what are the range of values that we expect for the arguments for this function and so on. But definitely I don't think, a general predicate is going to be a scalable solution, but some kind of measured approach. That measured approach will of course depend on what are kind of context that the compiler transform optimization engine is using, right? I mean, basically our encoding of the context needs to be and we are done if it's as good as what the optimizer is using, and that should be the first goal perhaps. So that's what we'll probably do.
Yeah, that's fair. That's a good insight to work with. Yeah.
Thanks.
Any other questions? If not, let's all thank Saurav. Again, great talk. It's lovely to see here these surveys of work done over long period. I'd love to hear more in the future seminars.
Thank you so much. Thanks, Venkat, and thank you to all my distinguished colleagues. I really appreciate your questions, and thanks.
Okay. See you all next seminar. Bye for now.